of all, I'd like to thank the organizers for the kind opportunity to let me present here our work in Lattice Qcd about in medium heavy Cooconia. And you see this collection of papers down here in green, something about relativistic bottomonium, in gray, something where I have not worked directly about non-relativistic bottomonium. And finally, in red here, the calculations of static heavy Cooconium in Lattice Qcd. So, and that's why we start with a small motivation, which we essentially don't need here, and then sort of walk through these various aspects of heavy Cooconia with finite temperature on the lattice, and finally bring everything together to a close. So the idea, of course, for looking at hard probes is hard probes are produced in the initial stages of the collision, and therefore, if you sort of look at the hard probe, it has seen all of the different stages of collision, and therefore they're the only accessible microscope to the early time dynamics of the collision. And that just evolves through all of the stages. And so we want to sort of address the question, what happens to Cooconium if we increase the temperature? And this idea is pretty old. So it was first brought up by Matsui and Satz about 35 years ago, now with more than 3,000 citations. And the idea was take a potential model to describe Cooconium. And then if you have Debye screening, there will be screening radius. And if that screening radius gets smaller than the radius of the state in your potential model, the state should not exist anymore and should be dissolved. And therefore you would see Cooconium modification or Cooconium suppression as intertwined with as significant of QGP formation. And then you would sort of later on extend this idea by looking at the different radii of different Cooconium types, whether they're in the charm sector or in the bottom sector, and the bigger systems would sort of melt at lower temperatures, and therefore you would be able to use Cooconium in QGP as a thermometer. In this case, you would look at color screening. This is something that has been studied on the lattice for ages. You look at polycurve loop correlators. Polycurve loop is essentially an infinitely heavy quark that is just sitting there. You have two of them at a fixed distance r, and you just sort of look at the r dependence and the temperature dependence to understand what is going on. That can be decomposed into a singlet part here in green and an octet part in red. The singlet part would correspond to the static meson, and the octet part would correspond to some unbound state of two heavy light mesons or whatever other combination of what you could get in the plasma. And what you see in this plot over here, in that in black, the zero temperature static energy on the lattice continued here to very small distances. And you see that this color average free energy that is obtained from the Polyakov loop correlator approaches this zero temperature result at very small distances where there should not be much medium effects, but then very rapidly flattens off and just assumes a constant value. And this happens for all temperatures that we have considered. At larger distances, where you're sort of really in the range where this screening is happening, you'd have to think of, instead of singlet and octet, which can't be defined there anymore, you'd have to think of different contributions from different parities or charge conjugation eigenstates of the states, and this is something that can be followed essentially down to the crossover and look very consistent. And then you sort of realize that the contribution to these free energies and to the screening of these free energies at the crossover is actually really due to the string breaking that you have in QCD at zero temperature even. Now, 15 years ago, roughly, these ideas by Matsui and Satz were sort of shaken up when coupling results based on some EFT calculations emerged. So we heard something from Peter already. So the first calculation that sort of was published was by Lyon et al. It relied on the effective field theory called Electrostatic Qcd, where you assume that it's valid for inverse distance being of the order of the Debye mass, which is parametrically much, much smaller than the temperature. In this case, what they found is that the real part of the potential would be the same as a singlet free energy, which is part of the Polyakov loop correlator we've seen previously, and that there would be an imaginary part that is parametrically of order g squared times the temperature. Shortly after, an alternative calculation based on potential non-relativistic QCD was published, which assumed that you either look at very small distances where you have the power counting of PNR QCD, or you can also look at the somewhat larger distance having the power counting of electrostatic QCD. And this calculation found that at so short distances, the real part of the complex potential is just the vacuum potential up to higher order corrections, and the imaginary part has these g to the 4th or g to the 6th dependence on the gauge coupling, and here also some formally different R dependence and temperature dependence. And so what this tells us is that the weak coupling says that these dissociation effects due to these non-zero imaginary parts, even at very small distances, are important. And if you have dissociation going on, the question is screening even relevant? And since these are formally very different in terms of the parametric dependence of the results, that was a good case to sort of study this with lattice. So the idea for lattice is we take the QCD action, we discretize it on a grid, having quarks and anti-quarks living on the sides of the grid and the gluons on the fields in between. Then we sample this stochastically with high performance computing and then just sort of integrate this numerically. That's the main idea. So in order to be able to do this numeric integration, we need to use importance sampling, which forces us to switch from the real-time formalism to an imaginary time formalism in order to have this exponential of the action with a real prefactor minus the action instead of plus I times the action, which would be violently oscillating. And put this into a box to have an I cutoff for a finite volume. We have the finite lattice spacing giving us the UV cutoff. In principle, we have to take both the zero lattice spacing and infinite volume limit in order to get real physics out of it. But as long as these effects are small enough, we can live with whatever we get. So we have periodic boundary conditions for gluons in time and in space, anti-periodic for quarks in time and periodic in space. And these periodic boundary conditions in time imply that all of the simulations that we do are essentially at finite temperature, and the temperature is the inverse of the spatial extent of the temporal extent of the lattice. So A, the lattice spacing times NT, the number of points in the time. And so what does that mean? If we want to study the real-time dynamics of dissociation on the lattice, we have a problem because we can normally assess this only in a real-time formalism, but we are forced to use imaginary time formalism. And so this is not directly possible. And the idea would be that if we can compute the spectral functions from the lattice, which can encode the entire dynamics, we can learn what we can't directly exhaust because of the imaginary time formalism. So if you have bound states, they are represented by delta functions, the spectral function. If you have unstable quasi-particles, like decaying or dissociating Qcd, that would be some sort of regularized peaks that locally look bright weakness, but certainly sort of are regularized because all of the integral of the spectral function has still to remain finite. And all of these peaks would be sitting on top of some UV continuum, which is either due to scattering states or due to some sort of merged excited state contribution where the peak structures are overlapping. And at finite temperature, we get on top of this a substantial IR tail contribution that is sitting at lower frequencies than the actual grounds that we want to consider. In this case, the idea is that we can compute Euclidean correlation functions GT at finite temperature of tau, and this is related by an integral kernel to the spectral function rho at finite temperature of omega. And if we have this spectral function, we could then do with a Minkowski space integral kernel transform back to the correlation function in real time, or alternately, directly infer the property that we want to know from the spectral function that is obtained from the lattice calculation. Now, doing this inverse transform from the correlation function here to the spectral function there is quite difficult because we typically have order 10 or maybe 20 points for the correlation function, but we need to know the spectral function with at least order hundreds to thousands of different points in frequency space in order to get a precise picture of some relatively sharp structures. And so this spectral reconstruction is a very big challenge, and this is still not something where we have final answers in all cases. So there is one way to slightly circumvent this, and that is something that I want to discuss here. So if we compute these Euclidean correlated in imaginary time, what we get is that these correlation functions are towers of exponential decay. So each one has an overlap factor AI, and then it's sort of an exponential e to minus the energy times the time. At zero temperature, if you consider mesons, it doesn't matter that our quarks have antiperiodic boundary conditions, so we get the same energy levels if we go in the time direction or in the spatial direction. At finite temperatures, our time direction has to be so short, there is an advantage of going in a spatial direction because this one can still be very long. And so what we can do is we can compute a correlation function at fixed temperature in the z direction of the lattice. In this case, that is an operator that we just have to implement and then measure, and this is related in a somewhat complicated form to the finite momentum spectral function on the lattice. And as long as we have genuine mesons, we know that the lowest feature is a bound state peak of this form, so it's a delta function at the meson mass, and as long as this meson is essentially the same as at zero temperature, we'll get essentially the same energy in the large z decay of our correlation function. On the other hand, if this meson has already been melted, then we'll have a dependence on this square root of the squared pole mass of the valence quarks and a pi t squared factor under the square root. So if this mass would be very small, it would be linear in t, but here we have something, if we consider large mass quarks, we have something that looks rather like this square root term over here. So what we did here is we used a relativistic formulation for the heavy quarks, put explicitly bottom quarks with a relativistic formulation in the lattice. It's called highly improved staggered quarks for the interested experts, and then computed the ratio of the eta b mass at finite temperature over the eta b mass at zero temp. And what you see is that up to a temperature of about 400 to 500 MeV, this ratio to the zero temperature mass is essentially 1, which means that the eta b does not really feel much temperature effects up to 400 something MeV. And then you start to see that this is increasing, and we have here the curves for leading order next to leading order temperature dependence, and you see that it begins to behave roughly as you would naively expect. Here in this plot, we look at the mass difference between the scalar meson and the pseudoscalar meson in this sector. And what you see here at the horizontal line is a zero temperature value is difference, and you see again at 350 MeV, the difference is within uncertainties consistent with the zero temperature result. Then there is a rapid drop over the next couple hundred MeV temperature, and then it slowly keeps decreasing. This rapid drop here indicates the state is melting, and then this slow decrease after that is sort of a suppression of the finite temperature effects by the large masses of quarks. So what we learn is that the ground states of pseudoscalar and vector are essentially unmodified until about 400 something MeV, while for the lowest scalar and axial vector states, we have essentially unmodified behavior up to about 300 something MeV. Now, from this, we have not used any assumptions, but we don't understand yet what the melting mechanism is, whether that is screening or whether that is dissociation. So we continue with the next version of lattice heavy quarks, namely Lattice Non-Relativistic Qcd. In this case, you have a problem that your heavy quark mass must be at least of the order of your lattice spacing, and therefore of your inverse lattice spacing. Therefore, you cannot send your inverse lattice spacing to 0. You can't use two fine lattices, and you cannot take the continuum limit. As long as you want to fix the temperature and you want to fix NT, you sort of have some limits up to how far you can go. So here I like to talk about an NRQCD, lattice NRQCD study at zero temperature and with NG12 lattices that use extended operators. So what is the advantage of extended operator? If I have a local operator, which is delta function in position space, I have very large contributions also from very, very high momenta of the quark and anti-quark, or relative momenta between those. If I have an extended source, which looks roughly like a wave function or like a Gaussian, then the very, very high momentum contribution will be suppressed, and I get a much better overlap with the ground state. If I look at this at finite temperature, this is a big advantage because I don't have many points in the time direction to wait until the excited state contributions decay. So this NRQCD program was started by first comparing point sources, which have these very high UV contributions, and Gaussian smeared sources, which have suppressed these by a considerable amount. What was found in this case is that once one uses a new scheme to remove the ultraviolet part of the correlation function by estimating the ultraviolet part of the finite temperature correlation function as being roughly the same as at zero temperature, you could then sort of get a very, very mild time dependence of the correlation function, or the so-called effective mass of the correlation function, that indicated that the thermal width of these bottomonia is large and the mass shift of the bottomonia is small. Then the authors extended this work. They started to use operators that were modeled after Cornell potential eigenstates. Then they used the so-called generalized eigenvalue problem to optimize by linear combinations the overlap with the real eigenstates of the problem, of the QCD problem, and obtained lattice beta salpeter amplitudes. Once you have these beta salpeter amplitudes for at least two different states, in this case, that the epsilon 1s, 2s, and 3s, you can feed these into a Schrödinger equation and determine the pole mass and the potential, because you know these amplitudes and you know the energies. Now, if you look at the potential that they obtained and compare this, which is here in color for the three different states, and you compare this in the background to these black symbols, which give the static energy from Wilson loops, what you see is that within large areas, you get essentially the Wilson loop behavior out of the NRQCD correlator. And then they continued further and looked at the time dependence and temperature dependence of these beta salpeter amplitudes at zero temperature. And that's something that you see in this plot here at the side for two temperatures, roughly a factor 2 apart. So the lower one at the crossover, the higher one at 300 and above MeV. And you see that these wave functions for the 1s, 2s, and 3s essentially show no substantial temperature dependence at smaller times. But as you go to larger imaginary time, you see that the 3s beta salpeter amplitude becomes visibly modified. And if it's not visibly modified at small times, but modified at large times, that suggests that it should be a thermal width that is responsible, that sort of leads to a non-stable state. Now, that's interpretation from humans. We can also let an algorithm figure out what is going on. So people use these beta salpeter amplitudes, stuck them into a deep neural network, and let machine learning figure out what is coming out. And that's what you see in this work by Xie et al. So what you have here, these boxes are the lattice results for the ended mass shifts of the different states that you see here. The open circles down here usually are the leading order hard thermal loop predictions for the mass shifts, and the field symbols are what you get out from the deep neural network. So the deep neural network reproduces essentially the results that the lattice had obtained for the energies when you give it the beta salpeter amplitudes. And if you look at the widths, you also sort of see here the open symbols are the deep neural network and the boxes are the lattice. You see that it again confirms what the lattice had already told. So the real part of the potential from machine learning is essentially the zero temperature one, and the imaginary part is much, much larger than the hard thermal loop result. So after that, we sort of went on and tried to study this with static zirconium. Here, the idea is that you have a Wilson loop in real time. You can look whether that has a stable ground state. If in the large time limit, the time derivative becomes time independent. And since we can't do real-time calculation, we do imaginary time calculation. And in this case, for the imaginary time, it would mean like the black symbol showing here, that the so-called effective mass is becoming flat at large times. Now, with the same lattice spacing, we have a different values of T, so different temperatures. And what you see is, as we increase the temperature, this plateau doesn't show up anymore. And instead, it gets steeper and steeper and steeper as we increase the temperature. And that indicates that the stable state cannot be there anymore. So what we then do in order to get quantitative, we sort of look at this relation that gives us a spectral function. We have here the spectral function. Here we have the correlator with tau dependence. It would be the Euclidean correlator. Then we decompose this spectral function parametrically in terms of some lowest feature that is thermally modified, some infrared tail that comes from excitations of a vacuum in the background that is propagating backwards in time due to this periodic time direction, and finally the UV contribution. For the UV contribution, we do the same thing that was done for non-relativistic bottomonium. So we estimate this from zero temperature and subtract it away. And then we are left with something that contains only this contribution and the tail is what makes this bending down here happen. In this case, we can compute cumulants of the spectral function times the Laplace kernel over here. And the first cumulant is just the standard effective mass in lattice QCD, which is usually plotted. And then we can just take higher derivatives of this to obtain higher cumulants of this. And at this point, we have not put any assumption in there what we get. And the typical picture of this first Q-valent is something that is, once we subtract the UV contribution, is essentially linearly decreasing at small times and then starts to bend down very rapidly due to this infrared tile. So far with NT less than 16, we could, or up to 16, we could only get signal for the third 3 Q-valents, which means that if we include the fact that our ground state and our tail each come with a weight factor, we can sustain at most something like 5 parameters in our spectral function. And if we want to have any chance of getting higher Q-valents at small times, which are interesting for sort of understanding the properties of state, we have to go beyond this NT16, where we then suffer bad signal noise problems, as for example, also in the case with these transport coefficient calculation. We started recently a feasibility study where we saw now go to NT32 and even higher ones, but this is all very preliminary and it seems to confirm what we've seen with the causal lattices so far. So now we analyze these effective masses or these first Q-valents in terms of a fit where we approximate the Breit-Wigner that would correspond to a quasi-particle locally by a Gaussian that regulates the Breit-Wigner that we have to do with without needing too many parameters, and then add a delta function for this infrared tail. So this is a fit form. Here you see a result. In black you see these UV subtracted results for the finite temperature, effective mass. The green curve is fit, and if you repeat this for all temperatures and for all distances, you get a feature for the lowest feature of the spectral function that looks like this. You see, so for temperatures of 150 to 670 MeV, there is practically no temperature dependence, and is within uncertainty, essentially the zero temperature result for the static energy or for the potential. If you look at the width, we have used here a Gaussian, so we have to rescale this width in order to make it comparable to the width, yes, to the width of the Breit-Wigner. And you see something where the width after dividing by temperature as function of RT shows totally trivial naive scaling. So after in these units, there is practically no temperature dependence left anymore. Now, this Gaussian approximation certainly is an assumption. We could also use something else. And something else would mean that we go back to the Hart thermal loop calculation by Line et al. If you look at the spectral functions that are coming out of Hart thermal loop, then we have these local Breit-Wigners sitting on some continuum here for almost 700 MeV and 4 different distances. So this is attractive because it should be a Breit-Wigner, it should be somewhat regularized. And since it's based on recoupling, you might have a try with this. The correlation function, or rather the effective mass that you get from this HTL result, is actually anti-symmetric about the midpoint of the lattice, where the Euclidean time is 1/2 the inverse temperature. And in this case, you would sort of get here the real part of the potential, and here in some somewhat complicated form, a contribution to the imaginary part of the potential. And we can now look at a subtracted correlation function where we took out the UV contribution from the lattice correlator that is not present in this HTL spectral function. And we compare here the lattice data in blue to the prediction by Hart thermal loop, where in both cases we've subtracted the singlet free energy in order to get rid of some issues which pertain to the fact that both of these quantity has affected by renormalons and sort of has a divergence on the lattice. So what you see is that the Hart thermal loop result has an anti-symmetry around the midpoint, which we do not see in the lattice result. Therefore, if we want to analyze in terms of this Hart thermal loop idea, the lattice result, we have to restrict ourselves to a very, very narrow range around the midpoint where results might still be consistent with this anti-symmetric condition that we have for the Hart thermal loop result. So we do these fits using only the 3 centermost points. This is sort of the ansatz that is used for fitting, and what you obtain in this case is a potential that as you go to higher temperatures sort of becomes flatter and flatter and flatter as a function of R, and therefore indicates substantial medium modification in the real part of this quantity and the position of this peak. And if you look at the width, that parameter that you have over here, what you find is that you do not get the naive scaling of the widths with the temperature and RT as we had previously, but instead the scaling is weaker as if you had powers of the coupling here in front of that sort of come with the widths. We then use, besides these 2 methods, 2 further ones. One is called the Pade rational approximation, where we interpolate the lattice, where we first Fourier transform the lattice data to imaginary frequency space, then interpolate, then analytically continue to real frequency space, and then directly obtain results for the position of the lowest feature and for its width, or the Bayesian reconstruction, which I can't go in detail here in the brief discussion. And what we now see is that at low temperatures, at the crossover, all of these results that we get are essentially consistent. Here in dark gray, you have the 0 temperature static energy, in light gray, the singlet free energy, which is screened at roughly 0.8 Fermi. All of these results are essentially consistent with vacuum physics. But you see a finite imaginary part in all of these results, which indicates that here dissociation of the Crocodium state is already at play, even at this very low temperature. As we go to 200 MeV, still very relevant for phenomenology at RIC, you see that the Pade and the Gaussian fit give results that are consistent with the 0 temperature potential. The HDL-inspired Baladata analysis is slightly lower, but is still not yet at the level where we would see the screening of the singlet free energy, the bi-screening that is very often assumed in model calculations. We still get here a result for the imaginary part that is substantially larger than it was at lower temperatures. And as we go to 400 MeV and so into the regime of LHC, what we now see is that some of the calculations are consistent with 0 temperature, while this HDL-inspired fit indeed looks very, very similar to the bi-screen singlet free energy. And all of these results find finite values for the imaginary part that are quantitatively important and get bigger as we increase the temperature. So to summarize, the lattice tells us that the modern picture of Crocodium suppression should be that dissociation is certainly very important for it. We've looked at spatial correlation functions of relativistic bottomonium and found that the ground state for eta B or the Y1s survive at least up to about 400 MeV, while the Chi-B0 or the HB are already gone somewhat earlier. When we look at non-relativistic bottomonium, where we can't go as high in temperature, we can sort of use extended sources and beta-theta wave function to boost the resolving power. And then we find spectral features where there is a very, very small mass shift for the bottomonia and a substantial width for the bottomonia. If you go to the static limit, where we keep these at fixed locations, we decompose the spectral function and we do model-independent cumulant analysis and find evidence for a large thermal width and then analyze it with different methods. And we find that indeed we can't make a clear statement whether it is screened or not, but we can definitely make a statement that the imaginary part, which leads to dissociation, is important already at the crossover. And these calculations are being improved over the next years. And so in 5 to 10 years, we hope to really have first principles answers for these questions. Thank you.
Okay. Thank you, Johannes. Now we have plenty of time for questions. So let's see whether there are questions from the audience here. So we have a question from Mine. Min, please go ahead.
Hello. Yes. Very, very nice talk. So the basic conclusion, if I understood correctly, it's there's almost no screening on the real part of the potential between heavy quark and anti-heavy quark, but there is a large width that corresponds to, say, the imaginary part of the heavy quark potential. Right?
So currently it's not yet totally unambiguous. If you look at this plot at 400 MeV here, you see that this HDL-based analysis gives you a result that is almost consistent for the real part with the singlet free energy, as it is usually used in the bi-screen potential model calculations. And if we switch away from this HDL-inspired analysis and use another fitting model, but sort of expand around the midpoint, we get in the Euclidean time direction, we get more or less the same answer for the real part and for the imaginary part. So it's not yet completely clear what the lattice says, whether the potential is screened or not, but it definitely has a non-vanishing imaginary part. And I think it's definitely something that should be included in all models for the interaction of QQ bar in the thermal medium, that this imaginary party there, this dissociation contribution, is really important. It's something where we even sort of pointed to right at the crossover, that this quantity, it's much smaller than at higher temperatures, but it is definitely there, and it should not be omitted. I think that sort of, it might sort of look like you get with the device screened potential something that looks sensible, but it seems that the microscopic dynamics really wants to have this dissociation contribution.
Sure, I'm not surprised that there is a significant, a very large width corresponding to the imaginary particle potential, but I'm quite surprised by your finding that that's almost no very weak screening up to temperature like 300 MeV or 400 MeV. Then if there's no almost or very weak screening on the heavy quark potential, but on the other hand, the lattice results, including your current results, there is strong screening on the free energy that's already occurs near TC, right? So,
so near TC, the screening that you see in the free energy is actually due to the standard string breaking. So the vacuum string breaking, where your sort of heavy quark anti-quark system can dissociate into a heavy light meson on one side and an adjoint or a sort of the daggered heavy light meson on the other side. That is something that is possible in the operators that you use for computing the free energies, but you can't see it in the operators that you use for computing the potential and the static energy. It's just because the overlap with different states. There is this overlap with this is just associated case. And so one of the problems probably with the screening is that the question is whether the quark anti-quark pair has enough time to rearrange according to some modified interaction, or if it sort of dissociates and decouples before actually it sort of could rearrange according to a modified potential. I think that is one of the ways to phrase it, that it apparently seemed that the dissociation happens much faster than the time that would be needed to rearrange. And of course, with a singlet free energy, we consider the static case, and there we have as much time as we like.
Okay, this is some physical interpretation between the difference of free energy and then potential. Thanks.
Thanks for the questions.
I was wondering whether from the experimental side there might be some measurements that may somehow help constraining better, I mean, adding some information that may also help in this direction to then have to discriminate better between the two scenarios.
Yeah, I mean, one of the things that we essentially see that the lattice data that we get are essentially compatible with both scenarios. And the question that is not entirely clear is, if you look at this sort of first cumulant or effective method you have here, whether the midpoint here should be where you do the expansion, as you suggest, by hard thermal loop, or whether you would sort of do the expansion at 0 time. And in this case, you sort of get something that is manifestly close to 0 temperature, which you sort of see in this figure. So, I mean, if you have the 0 temperature value of the effective mass or meson mass over here, and you now subtract the V contribution, it must necessarily end up very close to here if you do this expansion here. But if you somewhere over here do the expansion, you see this gap immediately. And so it's not yet something where we can say for sure which is the best choice. And currently our hope is that if we sort of use much larger lattices, that which you see essentially in this figure, so we have this much larger number of points. We hope that this and potentially anti-symmetric region at the midpoint gets larger and encompasses more points as we go to a final lattice. And that would sort of be an argument in favor of expanding around midpoint. But if it doesn't grow larger, then that's definitely an argument against expanding around the midpoint, as hard thermal perturbation suggests. And I think that is sort of the big puzzle at the moment, what we should actually do in this case in order to make a statement whether we have the bias screening or not in the potential.
Okay, thank you. Other questions? Seems not, so let's thank Johannes again.